development of some anodes for the direct methanol fuel cell. There are some logistics why we have to look at the direct methanol fuel cell instead of the hydrogen oxygen fuel cell. I will come to it a little later. But the basis here is, as you all know, in the fuel cell development only two important aspects have to be surmounted. One is the membrane, another one is the most efficient anode. Maybe the cathodes are already, whatever is available can be used. So if I can go to the next one. So as you all know, first few transferences will be very elementary for you. So what is the essence of why we are interested in looking at the fuel cell compared to the other route that is already being used, okay, IC engines and other things. The most promising and the best way to convert the chemical energy into the electrical energy is directly going through the fuel cell rather than going through the thermal route. Whenever you have a thermal route, you know very well that the Carnot limitations are coming. Therefore, the efficiency, net efficiency will be very less when you compared to these fuel cells. This is a very elementary thing. We will not worry about it. Next one is it shows you. Next slide, please. Next one shows to you what is the situation of the fuel cells when compared to the batteries. Okay, even why are we not worrying about the batteries? Why are we worrying about the good fuel cells? Because batteries are already known technologies. But if you look at the energy density and the possibility of recharging and the continuous use, you can see that there's a scale shows here. We are now looking at something like this. The energy density, whatever per liter of the capacity of the fuel cell, we have to be looking at the quantities of this quantity. Whereas the existing most efficient batteries are all lying in the lower limits, 500 to 4,000. We are now looking around 5,000 is the quantity that is we are looking at it. Therefore, second thing is batteries require very much recharging, which is not a very efficient method, because when you every time you recharge, especially in the climatic conditions like India, recharging is not in a very efficient way. Maybe in Korea it is all right. Dangerous chemicals, as you all know, depending upon sulfuric acid or whatever it is. The internal combustion engines I have already talked to you. So therefore, essentially we are now looking at fuel cells as an alternative to the internal combustion engines as well as the batteries. Okay. Next one, please. There are few points which you are already known to you. They are efficient. As I told you, the efficiency can be anywhere from 60 to 80. Even you can go up to 90. Reliability is very high. Cleanliness, because it is only if you are going to combust only hydrogen oxygen, you will get the water only. Unique operating characteristics, I will completely later. The planning flexibility, that is the cells can be designed to the requirement that you want, whether you want a stationary power or a mobile power or whatever it is. Future development potential is very high compared to the other technologies. IC engines and other things have reached a stage. Next transfer. Now this gives you various types of fuel cells. I am not going to talk about it. Everything is more or less based upon the hydrogen oxygen reaction, except the direct methanol fuel cell, where the direct methanol is being combusted to produce hydrogen and carbon dioxide. Now I must tell you one or two points why we are looking at the direct methanol fuel cell at the moment in our institute. One of them is always the academic institution. Academic people want to be in the forefront, and if I start working on hydrogen oxygen fuel cell today, I will not be able to compete with the West. That is the one logic. Okay. Another thing is, logically, if you look at it, at the moment, this is my personal opinion. Logically, if you look at it, even if you have a hydrogen oxygen fuel cell, unless otherwise you surmount the problem of the storage of hydrogen, you are not going to be putting hydrogen oxygen fuel cell in the operation. Whereas the direct methanol cell, even the existing parts can be used, because the fuel tank can be directly used for methanol, and therefore there is in my opinion, at least in the developing countries and countries like us, one has to pass through the methanol fuel cell before hydrogen oxygen fuel cell is being used. So therefore, that is one of the reasons why, because we have to address our national problem also. Therefore, that is the reason why we are looking at the direct methanol fuel cell. But as you all know, whatever we develop for direct methanol fuel cell, it can be applied to other fuel cells. Therefore, the transition will not be so much difficulty when the hydrogen storage problem is available to, storage problem is solved. So therefore, that is one of the reasons why we are looking at the direct methanol fuel cell. At the moment, our aim is to get reasonable current and the potential. I will show you the characteristics. That is the aim that with which we are looking at it. In the direct methanol fuel cell also, there are, as I told you, there are two aspects that one has to look at it. One is the anode, another one is the membrane. At the moment today, I will only focus on the anode because you have to develop very efficient anode. Now you will ask me, what do you mean by an efficient anode? Okay. Now the major players in fuel cell today, they are loading platinum to the extent of 3 milligrams per square centimeter. That is the level of the loading that they could reduce. But this is very high from the point of the cost. Okay. If you want to have a small cost comparison, if you look at a kilowatt power, this is 1:10. Okay, the kilowatt power nowadays is around $300 per kilowatt, whereas if you go in the fuel cell route, it is $3,000. So therefore, unless it becomes $3,000, it will not be a competing process. Now, if I have to bring it to the $300, either I should bring down the cost of the electrode material that we use or the cost of the membrane. But at the moment membrane is a monopoly item or more or less manipulated or controlled by the DuPont's Nafion. Therefore, unless somebody comes up with a membrane, it is not going to be easier. Whereas the loading of the platinum can be reduced. But the point is the loading of the platinum has to be reduced from 3 milligram to 0.01 milligram. And also at the same time keeping the efficiency of the process at the same 3 milligram per square centimeter. That is the logic which we are using. Now you will ask me, what is the strategy that you are thinking of? Okay, you are simply reducing it by nearly 3,000 times the amount of the platinum that is loaded, but at the same time you want to retain the activity. The logic is like this. Even though they are loading 3 milligrams per square centimeter, major players, the active platinum is only about 10 to 20%. Remaining 80% is not active. Therefore, there is a logic that logically itself you can load lesser amount if you make all of them are active. If all the platinums were to be active, the amount of the platinum loaded can be reduced. So therefore, this means that all the platinum that we are putting on the support, whatever support we are going to use, has to be in a configuration, in an arrangement, in an atomic scale, or it should not get agglomerated. It has to be, the dispersion has to be very high. Dispersion here, what we are meaning by here is the particle size of the platinum particles must be of the order of 2 nanometers. That is the limit that you can achieve at the moment. That doesn't mean that is the limit. Okay, you can go to single platinum atom, but unfortunately, the moment you put the single platinum atom, the operating conditions will be allowing it to agglomerate. So that is not a good idea. Okay, even though you can put single platinum atoms. So therefore, you should load it in a way that it is dispersed very high. At the same time, the particle sizes are of the order of 2 nanometers. Then the agglomeration is not taking place and the stability will be there. This is the logic that we are using. If we can have the next slide, please. So this is a simple how the photon exchange membrane works. You don't have to see this. Go ahead, next one, please. Now when we use the, as I told you, we have to make a judgment over whether I have to use a hydrogen oxygen fuel cell or the methanol fuel cell. Already I have one reason why I have to do methanol fuel cell, because I am being in an academic institution. I also have to perform and make few papers. That is one logic. Okay, with the competing with the Western world. Second thing is, as I told you, I have a national goal of looking at the transition, because from the petrol or diesel or oil-based situation, going to the gas-based situation is going to be a very high, because the distribution problem will come. Because we are not yet ready for the distribution problem. Now we have enough petrol pumps and things, but the distribution problem for hydrogen will be there. Therefore, the infrastructure, even though I may be reducing the fuel cell cost to be $300 per kilowatt, the distribution system will not take over immediately. Therefore, that is not going to be a possibility. That is why one of the reasons why we are looking at the liquid fuel as the methanol. So these are the reasons. Next one, please. So essentially, look at it. If you look at it, you will assume you will be able to see here. You only concentrate on this all other things are known to you. You can see that the energy density, from the point of view of the energy density, hydrogen and methanol is 1/6. You must understand this. This is the point that is, we have to be very careful. When I talk to you, you should not think that methanol will be producing the same amount of the efficiency, energy, density as the hydrogen. definitely hydrogen will be producing 6 times higher energy density than the that is because of the hydrogen combustion reaction. Okay, because here it is combusting to give rise to waste product of CO2, whereas that is combusting to give rise to H2O. Therefore, the energy density wise, we should not be going on talking that methanol fuel cell is the best. As I told you, there is a reason why we are doing methanol fuel cell, because we feel that the route to the ultimate hydrogen oxygen fuel cell is going to be through methanol fuel cell, because the infrastructure cannot be overnight changed. But we are aware that the energy density of the methanol combustion reaction is going to be 1/6 of the hydrogen oxygen fuel cell. That is one of the reasons why people are always thinking that the hydrogen oxygen fuel cell is the best. Okay, that is the reason, nothing else. Okay, there is no doubt about it, because the energy density is 6 times higher. Next one, please. So therefore, as I told you, among the if we can go behind once again. If you look at it, there are other options. There are 3 other fuels. If you don't have to go. The other options that are available are 3 other options: methanol and few other fuels that are possible. But among these, as I told you, the methanol is the highest. If you have seen that table, hydrogen, oxygen, hydrogen, methanol. After that, only the other ammonia, hydrogen, and other things are coming. So therefore, why methanol? Why not we take other things, methanol, ammonia, and other things? One is the high energy density among the liquid fuels. Okay, among the liquid fuels, this is the highest energy density. This is a clean liquid fuel compared to the ammonia and hydrogen and other things. Largely available at the low cost in various countries, including India. Easy to handle and distribute. It can be produced from the methane, zinc oxide catalyst to produce the methanol. We will not go into the details of that. Possible direct methanol operation fuel cell even in the stationary application, like laptop or cell phones and things. If it were to be an operation, it's only a capsule that is required. You simply remove one capsule and put another capsule. It will be able to do. This is an economically viable option at the moment. Next one, please. So this is why there are elimination of. There is another bigger advantage in using the direct methanol fuel cell is that if you are going to use hydrogen oxygen fuel cell, you have to produce hydrogen. Now, at the moment, the hydrogen is produced by a reforming process. Okay, ultimately, I do not know. Our friends may bring up some photocatalytic process or photo-assisted catalytic process, whatever way they want. But essentially, if you have to develop a fuel cell, it has to have an external fuel processor for producing the hydrogen, because the sulfur content must be less, carbon monoxide content must be less, and all those things. Then the hydrogen oxygen fuel cell has got a very great water balance. As you all know, the electrodes and the membranes cannot be allowed to dry out. Therefore, the humidification is you have to do an extra humidification on that. Whereas when you go to the direct methanol fuel cell, you don't have to do that, because the water that is produced is enough to keep the system under the wet conditions. Comparatively, at the moment, my impression is that the direct methanol fuel cell will be cheaper compared to the hydrogen oxygen fuel cell. Then it can use the existing infrastructure. That is what I am telling you. This existing infrastructure can be easily adapted to the methanol fuel cell. That is the logic that we are using. Next one, please. But the problem here is, as I told you, essentially the main problem is the anode. Okay, the methanol that we are sending in, 100% it should combust at the anode itself. If it is not combusting, already you are using efficiency, and then if you are not combusting, it is carried over to the cathode, and the cathode reaction is. So therefore, we have to now look at a great length the poor anode kinetics that has to be controlled. Fuel crossover is one of the problems. It goes to the cathode that we have to look at it. Essentially, all of them is controlled by the electrocatalyst. If I were to do an efficient electrocatalyst, then all these two things can be surmounted, because if I were to combust all the 100% of the methanol to anode itself, there is no question of crossover there. So therefore, this is the logic which we are using at the moment, but that doesn't mean that we are going to achieve 100% electrocatalytic reaction, but at least we will improve the kinetics so that the amount of the material that will be wasted, unburned or crossover will be less. That is the logic. Next one, please. So essentially, if you look at the challenges that are facing, one is reduce the amount of the expensive platinum. That is, I have already talked to you how we will do it. Then the next problem is, as you all know, when we buy a fuel cell and put it in operation, it should run at least 40,000 kilometers. So therefore, within that time, the platinum should not get agglomerated. Then the crossover is another problem. Then the improving the oxygen reduction kinetics is for the cathode. We will not at the moment look at it. And then design chip and electrode membrane. Okay. So essentially, what we are looking at it is this aspect. If you look at it, these are the two aspects that we are going to look. Is increase the utilization of the platinum. As I told you, 80% is being not used, only 20% is being used. And then by using the binary or ternary systems or supported systems, is it possible to increase the stability of the system? That is what we are at the moment looking at it. We will only concentrate on this aspect. Next one, please. So therefore, essentially the objective of this work is, as I told you, I have to increase the utilization of the platinum and then increase the stability of the system. That is all. So therefore, what we proposed was, we will produce carbon nanotubes or any nanomaterials where we will be able to disperse, and then load these platinum or platinum lithium or platinum tungsten oxide or platinum vanadium oxide we will complete, and then use these as the electrodes. Can you go further? The carbon nanotubes are all known to you, so I don't want to talk about carbon nanotubes. Next please. The essential reason being that the support, as I told you, platinum as such I cannot use because it is going to be wasting. Even when I have supported 80% of the platinum is not being used. Therefore, there is a need for a support. Next one, please. Therefore, we will not worry about it. So, therefore, the criterion that we have used is that they should have a high electrical conductivity. I will show you one or two transparencies at least at the end to show you what are the other possibilities of the support. High resistance for strong alkaline and acidic conditions, low weight, high porosity, high dispersion and high surface area. These are all very general characteristics of the support. Next one, please. So therefore, if I were to take the metal catalyst, what we can do is we can go into the monometallic system or a mixed metal system and then put them under unsupported condition or the supported condition. We are not going to look at this option because we are already told you that we are wasting even at the supported condition 80% of the metal. Therefore, unsupported is not going to be useful. Therefore, if I were to take the carbon supports, there are various ways of looking at it, carbon or the conducting polymers or CNT. Today we will only concentrate on this, we will not worry about this. This is a conventionally used support, carbon. Okay, we will only look at these two supports. The next one, please. So carbon as a support is already known to us because it is a conducting property, therefore it can be directly put, and then the surface properties, hydrophilicity and hydrophobicity can be controlled. Next one, please. Now, why carbon nanotubes instead of the carbons? Okay, suitable electronic properties as just like that of the carbon, so therefore it is possible. The mediated electron transfer reactions and the electroactive species in solution can be easily controlled here. That is one thing. The carbon nanotubes are the conducting polymers. Okay, they are stable. I will show it to you. And then they have the necessary thermal conductivity because there is a combustion reaction. Heat is being liberated. Next one, please. So therefore, this is only to show you what are the logistics people have used as the carbon nanotubes as the catalyst, not for this, even for methanol oxidation, not for the electrode applications. Next one, please. So therefore, if you look at this is the primary data that we have to generate. Okay, this is the platinum XC72, which is the commercial catalyst today available. These are the polarization curves. One of them is how the voltage is varying with respect to current density and the polarization. You can see whether the carbon the best available commercial carbon support and the carbon nanotubes are more or less matching very well. Therefore, showing that the carbon nanotubes can also be used as these simple carbon nanotubes. We will not take that into account. These two curves will show you the potential drop as far as a function of current density. This gives rise to the power density as a function of current density. So essentially, if you look at it, carbon nanotubes appear to be matching with the carbon XC72, which is the commercial support today being used. The catalyst used is 28% of platinum, 10% of ruthenium. Okay, this is the commercial catalyst that is available today. Okay. Now, next one, please. The proportions. Okay, this is also to show you more for the oxygen reduction reaction. We will not whether you use it in the methanol oxidation or oxygen reduction, the functioning is very similar. Therefore, the carbon nanotubes can be easily replaced in the XC72 as the support. Next one, please. Now the next 2 or 3 transferences we will quickly skip through. These are the methods of producing carbon nanotubes. You go ahead please. Next one. Next one. We will show you next one. We will show you this is to compare. Okay, what is the method that you follow? What are the qualities of the nanotubes that you are getting? These are all already known to you. So we will not. We will show you next one please. So at the moment, the best known anode material is platinum, ruthenium and carbon. So we are now looking today I will show you to you platinum, ruthenium and carbon or platinum tungsten oxide on carbon nanotubes. So this is what the significant progress is. Essentially what we are looking at is reducing the levels of the platinum, increasing the stability of the electrode, and then these are the materials that we are looking at. Okay, next one please. So therefore essentially only one thing I will show you, but there are many more things. We will not look at it. What we have tried to do is we have tried to produce these carbon nanotubes in a slightly different manner. In a case, it's a wet chemical method. Okay, it's a very simple method. Now what we did was this is generally used for all the other things. Only the polymer we use that is different. We have used phenylacetylene as the precursor, and then used a template here, and then phenylacetylene and the necessary polymerizing agents and other things were used. Then the polymer is allowed to be polymerized, the monomer is allowed to pass through the template and gets polymerized in the template. Okay, all the concentrations are given here, we will not worry about it. Then once the polymer is formed, the template is now taken and carbonized. Okay? That is one way. Or you can still do, if you want to load it, I will show it to you later on. I can load the platinum and then carbonize. So all kinds of possibilities are there. So you will be able to produce the carbon nanotubes. So I will show it to you the quality of the carbon nanotubes that we are producing. It's a very simple method. You will be able to. I have as a matter, you don't have to buy a very complex template of aluminum membrane and things. We have originally used aluminum membrane, but since we had availability of the mesoporous materials being produced by us, we simply use mesoporous materials. You will be surprised we can produce milligrams and even 100 milligrams, 200 milligrams of carbon nanotubes without any. What we did was, you carbonize the carbon nanotube, simply dissolve away the membrane in 48% HF. Then the remaining material will be the carbon nanotubes. So therefore you see, this is a strategy, but various variations are possible. I will show you how the platinum can be loaded. And next one please. So for example, we wanted to produce only one of them. I will show it to you. Platinum tungsten oxide. The essential logic here is the carbon monoxide being the poison for the platinum catalyst. Therefore, the tungsten oxide is capable of having the hydroxyl groups. Therefore, essentially promotes the carbon monoxide oxidation to carbon dioxide. That is the logic that we have used. So now you will see how this has been done. Okay? You will simply take the carbon nanotube that is produced in the aluminum membrane without removing the alumina. Then you put the phosphotungstic acid and then do this. Then finally you dissolve away the membrane. So now you have the carbon nanotube loaded with the platinum and tungsten oxide. So therefore this can be, I will show you also how it can be done, the electrodes can be produced. So final step will be the dissolution of the ammonia, dissolution of the template. Okay. So next one please. So there are various ways of doing it. This is the initial membrane, carbon nanotubes that are produced, the temp pictures of it from the polyphenol acetylene. Next one please. I will show you good quality carbon nanotubes that are produced. Next one. This is a high resolution temp pictures of the carbon nanotubes that are produced. Next one please. Now you can see here, okay. This is the platinum that is loaded on the carbon nanotubes, or platinum tungsten oxide filled on carbon nanotubes, produced in one single step. Okay, you simply take the phenylacetylene, and finally you will get when you are dissolved the membrane, you will be getting the material. Okay, this is how this has been happening. You will be surprised. You can see that the platinum dispersion is so beautiful here, and the platinum particle size is already the limits that we can reach. 1.2 nanometers, but anyway there must be an error on this. Therefore it is, let us assume 2 nanometers. That is the limit that one can go. Even when you put platinum ruthenium, people have seen already, when they put a bimetallic system, the particle size is very high, whereas here the particle size is almost the same quantity. Whereas when we went to the putting platinum tungsten oxide system, the quantity size is slightly higher. This is the problem that is we are having at the moment. We have to surmount this. But anyway, essentially what it means is that this method of producing these carbon nanotubes loaded with the platinum or platinum ruthenium, we are able to get the electrodes which are very nearly to the limit of the dispersion that we want. We have to only show whether we will get the current density and the potential. That is the next question we have to answer. Next one please. So this is only to show you that when we are loaded, whether we have loaded it correctly, whether we had the better platinum in the platinum 0 state, tungsten in the tungsten 6 state, in the XVS and the things. These are all only the conventional way of characterizing them. The next one please. So now from this I have to make the electrode. Okay. There must be some technology transfer must be there. So therefore briefly I will tell you how we have done this. The carbon nanotube loaded with platinum or carbon nanotube itself. These are all only to make sure that the electrode is made very well. 5% naphthalene in 200 microliter of distilled water, then ultrasonicated and then put it on a glassy carbon. Then you have produced this loaded or unloaded electrode. Now you are having the electrode. Okay. These are all only single cell experiments. Don't come to me and ask me whether this is only, first of all we are only producing the anodes. Okay. Next one please. So therefore the electrode is available at the moment. Now look at the current densities. That is the next job you have to look at it. So therefore we can look at it, the current density. This is look at this. This is enough better for us. This is simply a carbon nanotube material. This is, you can see that now the more it is in presence of methanol, you will see how beautifully the current is increased. When compared to the same amount of the platinum that I loaded on a carbon electrode, current density will be around 10 milliamperes something. Now it is around 70 milliamperes. The maximum current that is required here for a viable proposition is of the order of 300. Okay. Already we are having about 100. I will show you better one later. This is on operating conditions in the normal situations where you are going to operate it. Okay, the sulfuric acid medium with 1 molar methanol. Now there are certain features here. We will talk about it. If you will see that this gives rise to a smaller current at a higher potential, it's because of the inhibition reactions that are taking over. We will take over, those are all chemistry, we will be able to do surmount it a little later. So essentially what we are now looking at it, we are looking at the electrodes which are at least now only 1/3 of the current that is required. Hitherto the fuel cells were looking at under times lesser current and things. Now I will show you some results where we have produced our currents of the order of 150 milliamperes. Whereas the maximum current that can be obtained in a fuel cell mode, single cell fuel cell mode, is of the order of 360 to 380. Next one please. So this is all to show you various ways, as I told you, that is all possible. So therefore this is, as I told you, you can see here very well clearly seen at higher potential the current is decreasing. That is because of the poisoning reaction of the carbon monoxide. So therefore we have to use carbon monoxide removing catalyst like ruthenium or tungsten oxide. Next one please. These are all to show you. So now you can see, you can compare, you can, as I told you, it's of the order of 10 units is the simple system. Now this is polyphenol acetylene, polypyrrole, various catalysts, tungsten oxide, ruthenium catalyst and platinum catalyst. Even when I take the carbon nanotubes, well, simple platinum is giving me about 14 milliamperes, whereas the carbon nanotube with the poisoning effect removing materials, we are able to get about 100 milliamperes. Next one please. Now this is again to show you, if you want you can concentrate only on this, the flow sheet may not be there. This is to show you there is a small problem here. You will ask me, what is the logic you used? Why did you go from polyphenol acetylene to polypyrrole and other things? There is a small chemistry in that. I will show you. I will just tell you. When you take a polyphenol acetylene, the carbon nanotube that you are producing is only carbon. Okay? Whereas when you use polyphenol acetylene, polypyrrole, you are also having nitrogen in the carbon nanotubes. So therefore the hydrophobicity is increasing. There is a nitrogen atom effect also is present. If time permits, I will talk about it. Now therefore what we have done is we have taken the membrane, the carbon source, that is the pyrrole is sent, polymerized here, then the carbonized here, then you produce the carbon nanotubes. Now next one please. This is the same thing we are using the platinum tungsten oxide. The method is being evolved. Therefore, next one please. This is only to show that we really had the polypyrrole inside the aluminum membrane. We will not worry about it. We will assume that it is all characterized well. Next one please. So this is the high resolution temp picture of the template that we have used, okay, because we wanted to make sure that we are having the carbon nanotubes are all of the same size. This is the view from the top, and this is the cross sectional view. This is the template that we have used. There is nothing to do with that. Okay, next one please. Now on the template, after that it has to carbonize, and then carbon nanotubes are there. From the top view, we can see easily the carbon nanotubes being present. Okay. This next one please. This is also to view. These are optimizing the conditions. What is the temperature that you have used for carbonizing? So 973, 1073 like that. Okay. It's all not necessary for us. It is only optimized. Next one please. You can see easily as a Johnson bag, all the carbon nanotubes are protruding to you. Next one please. These are all only to optimize this. Now you see the quality of the carbon nanotubes. You beautifully produce a single wall nanotubes with the transparency. You can see very beautiful transparency in these nanotubes. Next one please. Beautiful or not, I do not know, but anyway, transparency is there. Next one please. These are all to show you the various qualities of the nanotubes that are produced. Now loaded, platinum is loaded. Now you see beautifully how it is now. Now when compared to the polyphenol acetylene, now polypyrrole, you see how beautifully the platinum particles are loaded and dispersed. You can see here also the efficiency of the loading. Here you see we have now reduced the platinum tungsten oxide. If you remember, we could not reduce it to below 10 nanometers. We have reduced it to 4 nanometers here now. If we can reduce it to one more order, 2 nanometers, the efficiency can go up. Next one please. So from this polypyrrole, we also produce the electrodes. Next one please. I will show you why. There is a reason why we are doing it. This is the cyclical voltammetric response of the electrode. This is the bare electrode, and then this is the electrode that is being used in the platinum tungsten oxide or platinum ruthenium system. Now next one please. These are all to show you various conditions under which it can do. We are already, I will show it to you a little later. This is all against the silver colored electrode. Okay. The same operating conditions of the 0 to minus 0.4 to plus 7.5 volts. Next one please. This is only to establish that the platinum is in the 0 valence state, ruthenium is in the 0 valence state, tungsten is in the 6th valence state. All those things are the conventional way of using it. XPS is being used to next one please. This is also the same thing done to establish tungsten is in the 6th oxidation state. Because we are using various chemical reactions that can be reduction of the tungsten. People will say you have produced a tungsten bronze, and that is what is promoting the reaction. Okay, that is why we have to make sure that that's why. Next one please. So now you can see the activities. This is the commercially available activity. Commercially available electrode. Okay. Now you can see we are now, if we will look at only this column, we will not worry about all other columns. These are all only to show you, as I told you, we have reached a current of the order of 100 milliamperes. That is what I told you, 98.5. Probably with error it will be of the order of 100 milliamperes per square centimeter. So the essential thing is of the order of 360 milliamperes. That is all the maximum that you can get. Now, we forget about even this. You look at this. This is the commercially available electrode. Is of the order of 1. If the activity is assumed to be 1, we are now having an activity of the order of 50. If we had an activity of 300, as I told you, if we had an activity of 300, it is already commercially viable. Okay. This is platinum ruthenium commercial catalyst. This is the platinum. This is the E-tech catalyst, which is being used in many of the fuel cells today. When compared to them, definitely our system as a higher activity. Next one please. Now we have to also, next question we will ask is what is about the stability of the electrode, how whether the electrodes are stable or not. So here we have shown it that the electrodes are as stable as the commercial catalyst of the E-tech. We will not go into the details. This is the time scale and this is the activity loss. The activity loss is not it is as much as 56% in the commercial catalyst. Next one please. Now this is the cyclic automatic of the system in the direct fuel cell mode. You can see now the current what we are talking about. Okay. This is of the order of 100 milliamperes per square centimeter. That is the current density that we are talking. In the operating conditions under the normal conditions that are used, 1 molar sulfuric acid and 1 molar methanol at a particular scan rate, we will not worry about it. The electrode that is used is, as I told you, produced from the polypyrrole, not from the polyphenol acetyl. Next one please. Now you can see what is it that we have done, why this has happened. Okay, this is the question that we wanted to answer. So we were trying to estimate the electrochemical surface area of the carbon nanotubes that we have used, and also find out the electrochemical surface area of the carbon that is being used as the commercial catalyst. Now let us only look at these three values. You will see when we took the carbon, this electrochemical surface area is 0.01 square centimeter, whereas when we take the Nafion Hc72, it's of the order of 0.08, whereas when we put the carbon nanotube material on the same carbon, the electrochemical surface area is 25.25. So automatically 25 times I have increased the electrochemical surface area. That itself must reflect 25 times the current must be increasing. Okay. So that is the logic we have used. We will not worry about all these details. Can I have next one please? As I told you, when we produce polyphenol acetylene and then went to polypyrrole, what is it that we are doing? Is the question we were asking. There is more aspects of this nitrogen incorporation or heteroatom incorporation in carbon nanotubes. Let us put it like that. But we will not talk about it today. But we will only talk about with respect to the anode. You see the amount of the nitrogen that is containing. Let us assume that we are polymerizing the polypyrrole in a certain particular fashion with certain other things. Therefore, the amount of the nitrogen can be controlled. That is, for the moment, we will assume like that. We will show you later on how to do it. Now you will see how the current density is increasing. When the when there was no nitrogen, the current density was 10 units. I hope you remember. 14 units was the number. Now, when I put the 3% carbon, the current is already 80 milliamperes. When the carbon content is around 3 to 8%, it is already 98, about 100, 1/3, 300 is what we are aiming at. And then when we put 10 and above, it goes down. So therefore, there is an optimum amount of these heteroatoms that is necessary. Now this gives us a very tremendous thrust to produce heteroatom containing carbon nanotubes and also to keep them. Next one please. Is stable. So therefore, essentially, without going into further, the template-aided synthesis of carbon nanotubes using polypyrrole precursor yield a well-defined carbon nanotube. The higher electrochemical current response of the electrode based on carbon as compared to the Vulcan carbon and glassy carbon shows the higher available electroactive area. 25 times is higher. The temperatures are shown very easily that the platinum, ruthenium, platinum tungsten oxide are having particle sizes of the order of 2 nanometers and 5 nanometers, as the case may be, where the platinum, ruthenium and platinum tungsten oxide. XPS showed the oxygen states of the metals. The catalytic particles are strongly entrapped inside. Please remember that. I will come to you later on if it is possible. Inside the tube is reflected by the fact that the particles appear to be quite stable even after the vigorous treatment in the concentrated HF. The higher activity of the composite electrodes based on carbon nanotubes compared to that of the commercial catalysts suggest the better utilization of the catalyst particles. The chronoamperometric response clearly reveals the higher activity and stability of the nanotubes. Can I have 2 or 3 minutes more? Yeah. Please. I will show you few transparencies only on the conducting polymers. Okay. Next one, please. Go ahead. These are the other conclusions. We will not worry about it. These are all I made the correlation of the catalytic activity, percentage of the nitrogen that is contained. Already I have told about them. So next one, please. I will take only 3 minutes. As I told you, when we take the polypyrrole and polyphenol acetylene and then polymerize and carbonize them, instead of carbonize them, you simply allow them to polymerize in the template method and then use this material. Okay, therefore that is the logic we are using. You will be surprised that not only you are producing conducting polymer nanotubes, you will be producing many other configurations. That is the logic. And then when you are producing various other configurations of the nanomaterials, the platinum dispersion will be better. That is the logic we have used. Next one, please. Only 2 or 3 times I have. This is the electrodes based on template synthesized polymer supports. How to prepare them, we will not do about it. Polyaniline template, platinum will be good put. You can directly produce this electrode in one step, or you produce the conducting polymer and then load on the platinum. Next one please. These are only to show that the polymerization of aniline is taking place. Electropolymerization or commercial chemical polymerization can be done. Next one please. Next one. Next one, we will not worry about all these things. These are all only to show you that these materials can be used as electrodes for the fuel cells. Next one please. This is these are all the nanofibers produced from the conducting nanofibers, not conducting carbon nanotubes. Okay. Now next one please. Now this is the carbon, polyaniline. Okay. Conventionally prepared electrode. Conventionally you produce polyaniline, load the platinum. You can see how the response, there are so much of inhibitions of the carbon monoxide and the electrode. Next one please. Now this will be before and after the resolution of the template. Oh, this is the template synthesized method. You see how beautifully that the methanol oxidation is taking place. Next one please. So now essentially what we are now looking at it is the onset potential. This is the template synthesized polyaniline. This is the polyaniline conventionally produced polyaniline. You can see this is the current 14.8. It becomes around 50 milliamperes. Okay. Therefore now a factor of 5 is being increased. Now if next one please. Quickly, this is to show the stability of the electrode. Next one. This is only the polarization to show that the polarization and other effects of the activity is increasing. Next one please. There is not. This is the another thing. You will ask me whether I can put it in a carbon cloth, because ultimately you will ask me to put it on a carbon cloth to be used in an electrode. So therefore we have devised a method for producing it in the carbon cloth. We will not worry about it. This is polypyrrole. It's in a template method. Next one please. We skip few minutes please. Go continuously go. This is polypyrrole results. We will not show this. We will go to the polypyrrole. Go please. Proceed. Next one please. This is the carbon conducting polymer tubes that produced by the polypyrrole. Next one please. This is the cyclovoltammetric response of these electrodes that are produced from the polypyrrole. Next one please. Is to show you that the current efficiency is increasing. Okay, therefore the conventionally prepared polypyrrole is 40 units means polypyrrole. As I told you, it will give you actually a 5 order of a 5, a factor of 5 will be increasing. So 40 means to 200. Okay, that is what it is happening. Next one please. This is to show the stability of the electrode. Next one please. This is the polarization effects. Next one. Then we went to look at this is to produce them on the carbon glass, but here we have used polymethyl thiophenol instead of the polypyrrole or polyaniline. Okay. This is methyl thiophenol was used. Now next one please. This is the cyclomatogram of the polymethyl thiophenol. Next one. You see, this is the nanocones that are being produced. The reason is now, since this is cone inside cone, the platinum is going to be, the particle size of the platinum is going to be controlled, because just like an ice cream cone to ice cream cone. So the platinum size, particle size are going to be controlled, and dispersion is going to be very high, and therefore this capable of using. Show you next to the data on. This is only to show you the cones that are being produced. Next one. This is the response of the electrode produced out of that. Next one please. You can see what is that what we want. 35 is the conventionally prepared polymethyl thiophenol. 356 is the this is the aim. As I told you, from the beginning I have been telling you, 360 is the maximum that we can get, and you can see current efficiencies are already achieved because the platinum dispersion is very high.